So I'm Thomas Hauser, Director of Research Computing at CU-Boulder, so I'm one of the moderators. And then
Hi. Welcome to the Future of HPC Architecture panel. I'm Tiffany Trader, Managing Editor of HPCwire, and I'm happy to be co-moderating the panel with Thomas Hauser. So we have with us our four panelists here today, four experts from the HPC community, representing four of the world's leading HPC companies. We have Bill Magro, Intel Fellow and Intel's Chief Technologist for HPC software. And next we have Marc Hamilton. Marc is Vice President, Solutions Architecture and Engineering at Nvidia. He leads Nvidia's worldwide team of solutions architects and field application engineers. And next we have Jerry Lotto. Jerry Lotto is Director of HPC and Technical Computing at Mellanox. Jerry has more than 30 years of experience with scientific computing. He was an early adopter of InfiniBand and built the first HPC teaching cluster in Harvard's Department of Chemistry and Chemical Biology with an InfiniBand backbone in the early days of InfiniBand. And
the last one is Mike Vildibill. I hope I don't totally screw up your name. He is the Vice President of HPE, Hewlett Packard Enterprise Exascale Development and Federal Programs in the HPC Storage Group. And he's responsible for the project strategy for the Exascale project at HPE. Our background was basically, there's a race to Exascale right now, right? There's 4 countries, the US, China, Japan, and Europe. I mean, Europe is not a country, but the region, they collaborate on the Exascale project. And basically, the challenge is to increase the computational power by a factor of 10 and reducing the power use by a factor of 10. We could build an Exascale probably right now, but the power bill would be just not, I think it's in the order of $100 million per year if you build an Exascale system. So that's just somebody that nobody would want to pay. So we want to ask the experts basically a couple of questions. Basically, where do you see the high-end computing landscape in the next 5 to 10 years? What's your competitive edge, since you are all representing different vendors? And in terms of application, what new application and breakthroughs will be enabled? And we give all of you basically 3 minutes to start this off, and then we have additional questions. So maybe start from right to left. Mike, do you want to start?
Yeah, I need help understanding which side is right. Thank you.
Yeah.
Okay.
For me.
And so will there be slides?
You sent me the PDF. Which one?
Yes.
But there are so many slides in your PDF.
Oh, that's okay. I can do it without slides.
Yeah, let's do it without slides in your case. You have so many.
Okay. So
I can put.
So I will do this in 3 minutes with one hand behind my back. Okay. So we do believe Hewlett Packard Enterprise (HPE) has a very active development program underway, leading to exascale computing. We are leveraging many years of activity in the company around research projects, one of which you might see a lot on the web about, called The Machine. You can Google HPE The Machine and get a little bit of background. We believe that some fundamental changes are needed in order to get to exascale, and that's really our flag plant is Exascale. And there's some very important things driving those requirements. What is an exaflop, for example, a really good starting point? I went to the November top 500 list and added up all the systems, and it adds up to almost exactly 1 peak exaflop. The world has an exaflop computer today. It's called top 500. It's distributed around 500 nodes around the planet Earth. And trying to imagine that system, which consumes over 650 megawatts of power, trying to do the same thing in the 2022, 2023 timeframe with a system that fits into one reasonable-sized data center consuming 20 to 30 megawatts. That requirement alone is fundamentally driving a lot of development that we're doing in HPE, radical advancements in power efficiency, and it's really driving some very significant changes in system architecture, done in a way that we can maintain legacy and we can still run our favorite MPI codes, but also fundamentally addressing how data movement occurs within large-scale systems. And I'll finish by saying that one of the fundamental aspects, as you look out into future architectures, we're going to be spending well over an order of magnitude more power moving data inside the system than we are computing the system. And so in our view of the world, it's a system architecture play, it's a data movement play, it's a lot of focus on system architecture, silicon photonics, how can we get better and more efficient at moving data in order to build systems that can scale to that scale while also having radical reductions in power. And so we're leveraging a lot of research that's going on inside of HPE, and that's one of our competitive advantages. And I did take my hand out from behind my back. I hope that was okay.
Thank you. Yeah, this was great. Appreciate that. So I'm going to put up your slides. Hopefully.
So many of you have heard of Mellanox, I'm sure, but I know that a number of the students, we don't make consumer products, so I just wanted to explain a little about who we are. We are an interconnect company. We make end-to-end interconnect solutions, InfiniBand and Ethernet. This shows pretty much the array of products that Mellanox manufactures. What I want to talk to you about is a change in computing model that's going to be critical on the path to exascale. Traditionally, we had CPU-centric networks. The idea that the network was basically a passive component of a cluster, that data would be delivered all the way to endpoints in order for any computation to take place. I didn't pay Mike to set me up, but we're trying to move toward a more data-centric model for computing. By enabling network devices to actually contribute to the computational load, we can offload a lot of the computational capacity from the CPU to the network. Network latencies and network bandwidth is very basic, but even if we drive those things down to zero and make them infinite, communication frameworks like MPI, SHMEM, etc., take up a lot of time, 30 to 40 microseconds. With Sharp, we can communication frameworks and drive them down by another order of magnitude, down to 3 to 4 microseconds. I'll talk about that this afternoon in a much more detail. Overall, the offloads that Mellanox products enable, not only Sharp, but Shield for higher resiliency networks, RDMA, Core Direct, tag matching, GPU Direct, and then 2 novel products, Innova, which marries an FPGA with a ConnectX adapter, and Bluefield, which marries an ARM ConnectX adapter in memory, allowing for user algorithms to be performed on the network. This is our vision of the path to exascale.
Thank you.
So it's great to be here. My CEO, Jensen Wong, actually is sometimes the chief gaming officer. So we are a consumer company. If you're a student, you probably use our gaming cards. And they will contribute to exascale, and I'll explain why. But our CEO does read HPCwire, and so he read that I was speaking there, and he sent out a blurb to all his staff, and he said, make sure Marc has all the information he needs. And so someone from our OpenACC compiler group sent me a 20-page presentation. Said, great, you're speaking at the Rocky Mountain OpenACC conference. And I said, no, that's too many slides. Again, the things that the last 2 speakers said are very much in line. I think one of the things is, and actually related to OpenACC, is for exascale, you need a programming environment. It's no coincidence, or we were actually surprised about a year ago when the Sunway Light, the 100-plus petaflop system, largest supercomputer in the world, was announced by China using their own onboard processor. And they announced that they were using OpenACC to run HPC codes out on their system. And they later joined the OpenACC Consortium. So if you don't know what OpenACC is, you should stop by the booth afterwards and find out. As far as, how do we get to exascale? Certainly I think the way exascale has been defined, it's been by double precision flops, and those are super important, and we continue to push that forward. Our Volta processor, we started shipping, has 7.5 teraflops of FP64 double precision, and that's 50% more than Pascal, which we introduced only 1 year ago. So we continue to push forward that double precision in the same power envelope, about 50% a year. More importantly, the largest supercomputer in the world, about the end of the year, the Summit system going into Oak Ridge National Labs, it will be over 2 exaflops of tensor operations. Tensor operation is a reduced precision operation used in deep learning. Most of you have probably, even if you're buried in traditional HPC computational science, have probably heard about what's going on the data science in deep learning. And we actually don't think that anyone would build a deep learning system that isn't based on HPC technology, or an HPC system that isn't built on deep learning technology. In fact, Facebook just delivered a system of 128 of our DGX1 systems, over 1,000 GPUs, and it has a full factory quad-rail InfiniBand system for doing deep learning. And I'm sure any HPC site here would love to have a quad-rail EDR InfiniBand system. And one of the engineers that helped design that is Doug Holt, and he's over there in the black t-shirt, and he can go talk to you about it more.
Thank you.
Hi, good morning. Mike, Jerry, and Marc really set things up for me perfectly, so I almost need to say nothing, but I'll say a few things. I think Mike really hit the nail on the head when he talked about where power is going. We've done a detailed analysis of where the power goes. It's into data movement. So you've got to minimize data movement. That means you need programming models, you need compute engines that avoid moving data, you need fabrics that have very efficient protocols driven by the needs of HPC to minimize back and forth traffic, whether it be for payloads, for protocols, or just for regarding the integrity of the data. So these are the things we're looking at. Now, Intel's history has been to drive compute up and up and up. And we realized a few years ago that compute is actually not the hardest problem. It's everything that's wrapped around the compute, getting a balanced system, memory technology, fabric, storage. And so those are the things that we're really focusing on, and we're trying to approach this with a systems point of view, even though we're not a systems company, because we don't think you can get to exascale by working on components individually. Jerry hit a really important point, which is latency. It's not just about power. Every time you move data, you incur latency. And the farther the parts are apart in the system, or even within a node, you suffer that latency. He talked about getting things down to the order of 3 microseconds. We're doing the same thing, targeting what I think are even more aggressive goals. Finally, we think exascale is not going to look like today's systems in terms of usages. It's not just going to be simulation and modeling anymore. It's going to be simulation and modeling sitting alongside machine learning and artificial intelligence, sitting alongside high-performance data analytics, and not just the workloads coexisting, but actually interacting through workflows. So imagine an instrument that has a perishable sample. You're doing real-time analytics and simulation on that as the data comes in, and you're adjusting the position of the beam or the position of the sample to get the best data. Those are the types of workloads we're focusing on, and those have broad implications for systems architecture, not just in terms of how they coexist and connect through resource managers, but also how do we make those frameworks take advantage of the core compute and fabrics that sits underneath. So thank you.
Thank you.
All right, thanks, Phil. Well, surprising amount of agreement there in our opening remarks. Very, very cordial group you are. So we're going to move on to the harder. I just want to remind everyone, we will be accepting audience questions after this portion. We're also taking questions on Twitter, and the hashtag there is RMACC17 on Twitter. So let's move on to our next portion here, questions. You have 2 minutes each, and there will also be option if anybody has a burning desire for a rebuttal, for a 1-minute rebuttal. So we have all these emerging computing technologies bubbling up, quantum, neuromorphic, et cetera, thinking about things, Moore's law pressures and alternatives to von Neumann, the von Neumann architecture. There are many things here. The Exascale computing program has specified that the first machine targeted for a 2021 delivery will employ a novel architecture, although I understand it's not likely to be what we consider an exotic architecture. Where do you see these new kinds of technologies fitting into your plans for Exascale? And let's start with Bill.
Sure, thank you. So I agree. The target for Exascale has been getting pushed back and back and back, and I think 2022, 2023 was mentioned in the opening comments. The countries and entities that want to reach Exascale want to do it even faster. They want to do it by 2021. And just as I discussed the power analysis that we've done, I think everyone's done that analysis and come pretty much to the same conclusion, that something different needs to be done in the way we compute, the way we couple computation together. So from Intel's perspective, we believe it's critical to specialize. At the heart of Exascale will be highly data parallel computations, but you still have the need to be able to run the tiny lingering bits of serial code that must exist, and you don't want to get killed by Amdahl's law. So we're looking very carefully at heterogeneous architectures that allow us to go to extreme data parallelism. The other thing we're looking at is that data movement problem. How do you change the architecture in a way that you minimize data movement and maximize parallelism simultaneously? And from our point of view, that's critical to getting to Exascale within a reasonable power budget. That, of course, then needs to fit into layers of additional system technologies wrapped around the compute.
Okay, great. Data movement. Let's go over to Mike, because I'm sure you have a lot to say about that.
Yeah, absolutely. Data movement is certainly central. The question really raises a lot of very interesting things we could talk about, and in a brief 1 or 2 minutes. Earlier in my career, I was at an NSF center that deployed the first teraflops computer system in a non-classified environment. Back then, it was a really big deal. Back then, I can remember talking to media and explaining how many zeros are after the 1 to explain how many calculations you do in a second. And teraflop was a really big deal. And we're talking about exascale and exaflop, and I would say that this is fundamentally different. When we talk about exascale, it's not just about a next bigger machine and what crazy things do we need to do to make a bigger machine work. It's happening within the context of things that are happening in industry and in cloud, and that there's a real marriage between technologies and advancements we need for exascale and what's going on in the world around us. It's no longer treated like a very unique instrument that we build a few of and then we move on to whatever comes after Exa. And so, fundamentally, data movement is very important, system architecture is very important, but many of these things are done in the context of the requirements that are needed in very large cloud build-outs as well. And so I think it's very important to keep an eye on these technologies and the exotic technologies to make sure that what we are developing fits into a larger context so we can leverage the activities going on in the cloud sphere and in the IT space. And at HPE, we believe firmly that the technology roadmaps can get us to exascale, and we can do it in a way that we're doing it with harmony with other industries and markets that are doing very similar, very aggressive technology advancement. And so when I look at something like neuromorphic or quantum, they're very interesting, but they seem to be interesting ways to do a compute element, but they don't necessarily solve what I believe is a much more important issue, and that is data movement within the data center, within the cloud, within surrounding systems. So we have to really keep an eye on the larger context, and not just how do you get a floating point calculation done.
Okay. Jerry.
The idea of diversive or disruptive technologies like neuromorphic computing and quantum computing are absolutely enticing. You think about the human brain, 86 billion neurons, each with about 10,000 connections. In your head, you have about a couple of dozen petaflops. But the amazing thing is that you do it on a power budget of 20 watts. When we get there, then we can look at something else. But the path to Exascale is not going to be revolutionary, it's going to be evolutionary. And a key challenge, I think, that diverse technologies are going to bring are how to connect them together. Mellanox believes that the way to do that is through standards. The IBTA, InfiniBand Trade Association, ensures backward and forward compatibility, and Mellanox adheres to those standards, and we will be working on trying to connect every future generation of technology together in the most efficient way possible.
And Marc, what's your view on novel technologies, novel architectures?
So you spoke about first teraflop system. I remember, someone can check, around 2010, Hans Mueller, the late Hans Mueller, stood up and announced the first petaflop system and estimated 2018 we would get to exaflop. And so now we're at sort of 2021, and that's only 4 years away. And that's a lot of processors you have to have in production. So it really needs to be technology that exists today or will exist in the next year or two to get it in production. Nvidia strategy has always been on a heterogeneous computing architecture, having a latency optimized core, such as a CPU, combined with a throughput optimized core, such as a GPU. You see a lot of accelerator technologies today. It seems every week there's a new accelerator chip. Google TPU, for instance, being announced. So clearly the industry is looking at specialized accelerators, but we firmly believe that you need the combination of those. And furthermore, because of Amdahl's law, we believe that those need to be combined in such a way that you have so-called fat nodes, a large number of throughput optimized and latency optimized cores together in a single system to minimize that movement of data. You're always going to be able to move data faster on a piece of silicon or on a motherboard than over a cable over a network. So all of those are necessary, but throughput and latency optimized cores on a fat node.
Any rebuttals? Does anybody desire to respond to some of the points made?
I'll add a few comments. I mean, Jerry pointed out the importance of standards, and Intel agrees completely. We've been active. We were founding members of InfiniBand, and I actually co-chair the technical working group of InfiniBand jointly with Mellanox as reps. So Intel's a big supporter of InfiniBand. At the same time, as we look at it, what we see is that the protocols were not designed around HPC, and as a result, it also wasn't built for that scale. So while we're embracing standards, we're trying to do it one level up at the Open Fabrics level, and working through the Open Fabrics interfaces working group. What we've done with the community is define the exact semantics that are needed, and this frees everyone, Intel and others, to create fabrics that are the most efficient, highest performance implementation of what's needed to build an exascale system. And similarly to Marc's comment, you can get closer between moving from a cable to a motherboard. You can get further closer by getting on package and ultimately on die. So we think integration is a key technology to get to exascale.
Anybody else want to follow up? Okay.
Yeah, I'd like to underscore the importance of open frameworks and open standards, and back to my comments about we need to, exotics are great as tools to get specific computation done, but it needs to fit within a larger open framework and has to be relevant to what else is going on in the IT industry. And so certainly Hewlett Packard Enterprise also is very keen to drive things in an open system framework and driving toward open standards so that we can ensure that what we're doing in HPC space also applies and is relevant elsewhere.
Okay, thank you. Moving on to our next question. My computer is stuck. So I think we have a backup here. I think the interesting part, I think, for this audience too, right? Not everybody is going to work on the exascale. So what of the trends at the exascale will flow down to more like mid-scale systems that are deployed in kind of university centers or regional centers? And yeah, how do we make sure that kind of the long tail of science doesn't get left behind?
Thomas, can you see this posted up on your screen there?
Oops, no, I can't see that. I turned notifications off, I thought, but apparently not. Okay, so here's the question, but I think I mentioned that. Okay, maybe Mike, you start with answering that.
I think it's a really interesting question. I could maybe perhaps use an electron microscope as an analogy. Exascale, and again, Exascale is the flag plant. It's the thing that is really helping us focus our requirements and our R&D efforts and schedules towards something that's a single point in time. And I can think of an electron microscope, it's an instrument. One electron microscope costs a lot of money. You can only have so many of them. They're in very special places. And it's not the equivalent to 1,000 small microscopes. It's very limited. And it does something that you cannot do with 1,000 small microscopes. And so on one hand, with Exascale, we need to develop those instruments, those things that can solve problems that cannot be solved otherwise. It's very important. But it's also equally important that we drive the technologies as we go toward Exascale in such a way that they apply directly, immediately to other adjacent markets, the mid-range systems, but more so the enterprise and the cloud and the IT environment. And so all these customers, in our point of view, are being challenged by very similar challenges, and they care a lot. They care a lot about how much power they have to provide to run their system. Many in the enterprise and commercial space don't have the research teams to go off and start doing spreadsheets on what is the power consumption of their big system going to be in 5 or 6 years. But in the Exascale environment, we do have that luxury or that opportunity to live in the future to start thinking about these things. So we're identifying challenges at Exascale which are indeed precisely the exact same challenges that are going to be common through industry and common through mid-range systems. And so we see a great linkage between what we're driving toward at the very high end and what is needed at the mid-range, and in fact even more so what's needed in the commercial space.
The technologies I was talking about, for example, SHARP, Scalable Hierarchical Aggregation and Reduction Protocol, are applicable to clusters of every size using Mellanox technology. Our Switch IB2 EDR switches support this protocol to speed up MPI and SHMEM-PGRAS programming models for applications, whether they're running at terascale, petascale, or exascale. The key, I think, is going to be continuing to develop these protocols in order to speed up collective communications. And a new generation of SHARP is being developed now that's going to enable us to do aggregation of much larger packet sizes, enabling neural network type acceleration for AI and machine learning frameworks.
Well, I think you need both trickle down and trickle up, in that if you think about it, the Summit system, which I talked about, is several $100 million in over 2 exaflops of tensor, or over 2 exaflops of tensor ops. A single Volta DGX1 in 3 rack units is actually almost a petaflop of tensor ops, 960 tensor ops. But those instruments of science for data science in HPC start with just a standard GeForce GPU card, which you can buy at any store or at Amazon for a couple $100. And again, we have today 500,000 registered developers developing in CUDA in OpenACC, and I think that really long tail is super important, right? If you build an instrument that just 10 or 100 researchers can use, it's not going to be very powerful. So having something that is not only an open standard, but part of being open in the broader sense is available around the world and affordable by any researcher.
Share the I turned it on. Okay. Okay.
Yeah, so I agree with Marc. There's a trickle down and a trickle up effect here, and we need to pay attention to both. And if you just do the simple math and you imagine that an exaflop machine in the future is going to be maybe, let's say, 100 to 200 cabinets of incredibly dense, energy-efficient compute, just as an example. That implies a single cabinet is going to be in the range of 5 to 10 petaflops. What an amazing resource that would be for a research group, that you could have your one cabinet in a data center that's available to you and is affordable. But it's not just going to be about that. Exascale is about the efficient algorithms and actually getting application performance up, not a top 500 run. So there are going to be breakthroughs in the Exascale which are going to change the way we do science, and those will trickle down as well. So the overall efficiency of what you get out of that petaflop or 5 petaflop cabinet is going to go up. And then finally, for the Exascale, if you look at the problems they're trying to solve in the discovery, it is around tying together analytics, machine learning, and simulation. I gave one example earlier. Another one might be in an Exascale computation. You're generating so much data. What data do I keep? Which is interesting to analyze, and which can I discard? Because you can't keep it all. AI can play a huge role in that, and keeping data local through things like new non-volatile memory technologies that have emerged. Okay, that integration and the support of multiple different types of what I'll call future HPC calculations, again, will trickle down. And then if you look at what's going on in the research community today, I mean, I've seen some survey data, and I can't quote it specifically for you, but a huge number of research projects are actually integrating analytics and machine learning already into their science. So there's a direct connection there as well.
Go ahead.
Yeah, we have a question that came in from our Twitter feed that I think fits in here. Where do you see, how will HPC be used in non-traditional sciences, just social sciences, over the next 5 years? Anybody want to take that, field that? How will HPC be used in non-traditional sciences such as social sciences?
Again, all the sciences have huge amounts of data, right? And there's more and more data. You know, one of the big buzzwords everyone talks about is IoT, right? And people think of IoT as little tiny sensors that don't create a lot of data, but you know, think of that little tiny sensor in your cell phone, the camera, right? And all the data that can create. I heard the other day that if everyone on the planet spent just 1 minute a day talking to their cell phone, to Siri or Google Now, that would require the equivalent of 100 new web-scale data centers to be built around the world. Right, with CPU-only data centers, and hence the need for that acceleration technology. So I think that where that social sciences will make more use of HPC will be through the data science side of it.
Anybody else? Yeah.
Yeah, I'll just pile on. I agree completely, and I think what's different is that social scientists in the past have had to deal with, I'll say, existing tools that are not as capable. And when you bring exascale class computing and the innovations that will be driven around machine learning and analytics, those algorithms, and enabling them to run really fast on the underlying system architecture, that's going to bring the ability of the social scientists to start applying those tools to massive data sets, the ones Marc was talking about. And that'll be very new and very disruptive.
If I could add just one more thing, I think the HPC world has been talking about, Fortran will one day die. Fortran will probably be in the exascale systems, but the social science people are not going to write Fortran code. In fact, they're not going to write code at all, right? That's the beauty of deep learning, right? Is a deep learning algorithm is a software program that writes software, right? And that's why today is we're working with over 200 different organizations in self-driving cars, right? Because 5 years ago, only Google was working on self-driving cars because only Google had 1,000 engineers that they could have writing if-then-else code, right? Today, you go off and you buy a Toyota Camry and you put a few cameras on, and you're in the self-driving car business.
Anybody else wants to answer on that?
Okay. Moving on.
Yeah.
So we're seeing so much activity around AI and deep learning, and I've really been wondering a lot, and I think a lot of people are wondering what effect the AI and deep learning will have on HPC. So how will these new workloads influence the architecture of new computational systems in the next 5 to 10 years? And how would you address concerns over the potential disruptive impact of those changes? For example, optimizing for AI and tensor operations on established HPC applications. Let's start with Marc, who was going for the microphone.
I think that there's a lot of concern, and I get asked all the time, you're focused so much on AI, does that mean that you're dropping HPC? And again, just look at Volta, 7.5 teraflops of double precision, shipping today, 50% performance improvement from last year. You have to do both, right? Because you will have classic simulation, you will have classic computational science, and you will have data science, right? And in fact, if you have to move the data from an AI system to a computational system, right, then everything that we talked about doesn't work. You're moving the data and you lose efficiency. So you have to have a processor that is equally good at double precision and new reduced precision. And so again, we're on our second generation today of Volta supporting 16, 32, and 64-bit precision equally well in the same processor.
All right. Jerry, you're nodding your head. What do you think?
What everybody's been saying about data is absolutely true. Data-centric computing is definitely the way of the world. It's going to be key for AI. And our vision is that you should be able to compute on data wherever it is. If it's in storage, you compute on it in storage. If it's on a network, you can compute on data as it travels. And if it's in a CPU or a GPU, you compute there as well. The idea of co-design is sort of central to the concept of exascale computing. The idea that heterogeneous architectures can put together different computational architectures, and applications can then be distributed so that not just an individual application, but individual threads and individual workloads can be directed to the infrastructure where they're optimal. Mellanox is going to bring the network in as another co-processing element in this whole concept of co-design.
Well, I'm trying desperately to have a different opinion here than my colleagues, and so perhaps I can break away on this one. So we're very quite bullish on HPC, and when I look at the physical world around us, there's a lot of complexity around us. We have simulators and models that can simulate physical phenomena that happens around us, and it's an insatiable amount of computing we could do on the physical world around us. The only thing holding us back is that the computers to do that computation are either too expensive or too difficult to program, or you don't have access to them. And it's our belief that the more accessible and affordable and cost-effective and power-efficient HPC systems are, there's an insatiable demand for us to go and simulate the physical world around us. The human genome alone, 3 billion base pairs, we all kind of know what that translates to into all of the computation and data analytics that has taken place in the marketplace and in the world in the last decade, and that's the human genome. You look out at the farm, and the wheat genome is 5 or 6 times more DNA than the human genome. And wheat, supplies 30% of the dietary support for the planet. I mean, that's just one example. The things around us in the physical world that do need to be simulated with HPC methods and maybe even old crufty Fortran programs, that need will continue. Now, these other techniques like machine learning and AI will absolutely supplement that. It will complement it. It will accelerate it. We will use machine learning algorithms inside of HPC algorithms. We will use machine learning to help interpret data that comes out of simulations. But the core activity of scientific discovery through simulation, which requires the old, floating point arithmetic and maybe even crufty Fortran code, there is still a place for simulation, and it doesn't just go away with new methods. And that we believe the new methods will integrate with the former methods. They will simply not replace them all out.
So at Intel, we think the first step is actually recognizing and acknowledging that artificial intelligence and analytics are new HPC workloads, right? They're different, but they are HPC workloads. And that means you have to bring it into your thinking as you do system design, as you design your compute engines. The way we define HPC is around a few characteristics. One is it has to be computationally demanding. How else could it be high-performance computing? The second thing is that actually the product of the computation is insight or knowledge. It helps you get a product out sooner. It helps you understand the weather and a pattern in a time that's useful to you, right? And so on. So it's an intellectual product of the computing versus a lot of other things in IT. And the third characteristic we look at is when more computational resources are appropriately applied, do you get a more valuable result? You know, a 12-day weather forecast that takes 3 months to compute is useless, right? One that you can get in 12 hours is very useful. A better, safer car that you weren't able to design in time to intercept the model year is not useful this year. So applying more resources gets you a more valuable result. So what we're doing is certainly there are tensor engines and others that are dedicated to deep learning, but we're looking at deep learning along with analytics, visualization, and classic simulation modeling as things that all have to live on a single compute engine. So we want to incorporate those workloads and account for them, but we don't want to specialize so much that we're just duplicating. So that's the approach we're taking at the CPU level. Marc pointed out earlier that there are classes of workloads that can benefit from aggregation and larger coherent nodes. That's a clear trend in the industry, and it's a large departure from what we had with MPI and MPI OpenMP. So that's obviously something we're looking at. And the third thing I'll say is that we're looking very carefully at the role of non-volatile memory, because minimizing data movement means simulation needs to be able to leave the right data and enough data behind that machine learning and analytics can come and operate on that. And having that architecturally integrated and tightly integrated into the platform so the data's in the right place at the right time is going to be critical to the HPC.
Any other comments on how much specialized silicon AI will require and how much specialized silicon a market can support?
You know, there hasn't been really any long-term successful dedicated HPC silicon companies, right? Because HPC in and of itself, the classic HPC market, hasn't been enough to drive the billions of dollars of investment necessary to make a new processor. And that amount isn't going down, right? To make a new 10 nanometer mask, even before you build your first silicon wafer, is 10 or tens of millions of dollars. So huge investment in that case. So you need to have general purpose silicon, right? One processor that can do more than one thing and can be sustained by a large market.
And perhaps on a lighter note, I spend a lot of time in Silicon Valley. You cannot swing a cat in Silicon Valley without hitting a CEO of a startup who's doing machine learning silicon. Okay, and so the point is that there is a lot of innovation going on in this space, and members of this panel are very aggressively innovating in this space. And so there will be innovations and there will be changes. I think fundamentally what's important, however, is that we continue to think of these technologies as something that needs to fold into a larger whole. And getting us back to open, where we started this entire panel discussion with open standards frameworks, because the machine learning dedicated silicon or specialized silicon is going to be very important for everyone except for cats, apparently. I'm sorry for that analogy. But it's also very important that it integrate in with a larger data center framework.
I think what you're asking is a great question, because one reality that I think a lot of people aren't aware of is all the silicon vendors are dealing in their fabs with buying equipment from the same companies. We all have the same fundamental limits of how large a chip we can build. And that means we're all forced to decide how to use that real estate. So there's a key tension, which is if I come up with something that's a dedicated, say, a tensor engine that's wonderful, it's perfect for machine learning, I dedicate area to that on my die. By construction, I'm harming the rest of HPC, right? So what I need to do is what we need to do is find the right balance of what is going to benefit from the most from the deep integration of being on die, what can tolerate being on package, what can be on a motherboard, and what can be at the other end of a fabric. And that's where a lot of the tension is, and will limit how far people go in the direction you're saying.
So need to fine tune those knobs, just a disagreement maybe over where they need to be tuned.
Likely, yes.
Likely, yes. Okay.
Okay, I think this is opening up now to questions from the audience, and also looking at Twitter. So I see already. I think Dane, you were the first one.
So
we need a microphone.
I'm going to repeat it.
Do you want
Okay.
to put one in the audience and one for us?
Yeah.
Sure.
in the spirit of making a little controversy, I like definitive statements that may be wrong, but at least are definitive statements. Hardware's easy. Software is hard. Software adapts much more slowly than the hardware can adapt. We talked a little bit about how AI has allowed a revolution in programming models over the traditional if-then-else statement that was made. What's the new replacement for the remote procedure call that is the current solution for CPU plus coprocessor architectures? What comes next? What's more efficient?
Somebody else is reaching for the mic. I don't know that there's necessarily a replacement. I mean, the fundamental concept of a remote procedure call is you're asking an alternate compute engine to do something on your behalf and send the result back, and it has two parts, control and data movement, right? Both of those take latency, they take time, both of them involve data movement. So I think there's existing industry standards and other standards coming out of consortia, such as the OpenMP4, the OpenACC that Marc mentioned. We've got OpenCL. There's other frameworks as well. Those are likely going to be the way that people program when they're dealing with a distinct external compute engine. Intel's point of view is that we'd like to avoid that movement of data. We think the movement of data is critical with an external accelerator because it's too far from the memory otherwise. And that's why if you look at any external accelerator, regardless of what it's targeting, it's going to have some tightly coupled memory. That necessitates data movement, which in turn necessitates a burden on the programmer to identify and move that data back to your software's hard. So we're trying to do everything we can to avoid pushing you there unnecessarily.
Somebody? Any other comments to that question? No? Okay, I think we have a Twitter question. How can we support the integration of existing cloud and web workflows to take advantage of traditional HPC resources? I think we heard one example already, right?
Well, I think Microsoft just invested some money yesterday to buy a little company that did just that. I think, again, the move to the cloud is not new, right? The clouds have been building up for the last 10 years, and I think the question is not if workloads will move to the cloud, but it is when. So clearly there's a lot of work there for the integration. I think each of the cloud vendors have their own sort of self-serving desires to make it easy to move to their cloud and not to someone else's cloud. So that's certainly a challenge. And again, that data movement is really going to drive where if you do something in cloud or on premise or on the edge, right? Where it is, if your data is in the cloud, then it makes sense to compute there, and that's probably going to drive those decisions.
I absolutely agree with what was just said. The whole cloud is starting to dissipate. We're talking now about fog computing, where there's compute everywhere. So I think that compute models are going to be changing. It's not just burstable. It's distributed computing, anywhere data lives. That's going to be the key to future.
Yeah, I agree with all this. I think when I heard the question, I had two thoughts cross my mind. One was around the infrastructure operators and the importance of hybrid IT, where we can do on-premises computing where it's needed, where it really makes sense to be on-prem, and where we can burst or offload to multiple clouds as needed. And so the previous responses there, I think, were spot on. Another thing that crossed my mind, however, when I heard the question was along the lines of making sure that we don't, as an HPC community, that we don't become an island, a technology island. And it's also very important if we want to have relevance in the cloud space, we have to have a commonality in terms of the technology. We can't go off and develop technologies that are completely islandized from the rest of the world. And so it's very important that we develop architectures and we adopt technologies that are used in HPC but also used in the cloud, and it makes this notion of hybrid, we can seamlessly move between our on-prem and off-prem computing and data analytics much more fathomable, much more plausible when we are basing all of the IT on some very fundamental common building blocks.
Real briefly, I mean, most of the talk about HPC in the cloud is about how do we do HPC in the cloud. But people don't talk much about what is the impact of cloud on existing HPC centers. And I'd just like to point out that I think the expectations of users are changing, and there's an actual existential threat to people who run HPC centers if you don't start to consider and adapt and embrace the users who, their alternative to coming to you and getting an account, conforming their workload to your software environment, putting their application or their workload and their jobs in your batch queue and waiting. The alternative is they pull out a credit card and they go to Amazon and they get the resources they want in any quantity they want now. So I think HPC needs to be looking very carefully at cloud technologies and appropriately embracing them. There's a lot of them that can drive higher operational efficiency, but there are other directions in cloud like disaggregation, which will actually hurt and put us off the path to exascale. So we have to intelligently and appropriately adopt those. But most importantly, we have to create a way to meet the needs of those users who want to bring containerized workloads. So things like Singularity are steps to give people portals and other accesses that they expect. And finally, enabling higher level domain-specific languages, the things people are programming in now, Julia, R, Scala, and making sure those are supported and supported well in HPC systems is going to be important.
Okay, I think take another question from the audience. Pat here.
Yeah. So thank you for a stimulating session so far. I know why each of the four are you here. I'm struck by who isn't here, and that would be IBM. I remember their Cornell Theory Center was focused on AI and deep learning from the very beginning. And then again, we all know what happened with IBM and Blue Waters, but we're seeing these commercials for Watson on TV nowadays. So my question to you is IBM irrelevant in this space going forward? And Watson too?
Diplomatic.
I'll just speak for the group and say I don't think anybody's going to touch that question. We're all here to talk about what we're here. Just wouldn't be polite or professional to respond to that, quite honestly.
Yeah. Thank you. Yeah. I think we have another Twitter question.
We do. We had a. There's a little bit of skepticism about exascale. I've heard, people are thinking that maybe so-called hero codes or that there's too much machine. This question is why exascale? What could exascale systems do that existing petascale systems can't? Weather prediction. And let's see if the other one had any extra. What scientific HPC applications necessitate essentially the same question, necessitate the development of exascale. So why do we need exascale?
Well, I think you need to visit the grand challenge problems in every area of science. Chemistry codes, as a rule, if you look at the grand challenge problems in chemistry, those are exa or even zetascale to be simulated in any degree of accuracy. Brain science, healthcare, just every area of science has things, either simulations, visualization, virtual worlds that are needed in order to gain insight, which cannot be done today at petascale. The real answer is we don't know until we get there. A lot of the things that will be made possible by exascale will start pointing to the next generation. What can't we do there?
I agree completely. Just a couple specific. System optimization is something that's really driving exascale. So I was talking to some folks yesterday, and they're telling me about how it can model wind turbines. But what happens when you have a wind farm? You now need to optimize the whole farm, not an individual one. So you've got fluid dynamics, you've got structural mechanics, you've got turbulence modeling and interactions. That alone is an exascale problem. And then when you put on top of that, now you want to do an optimization. Right? Look at all the configuration space you need to explore. The same thing is true in climate modeling. We've gotten quite far in our ability to model the climate and see how, but now what if we want to go back and try 150 or 1,000 different scenarios of changes we could make on Earth and what impact it would have? you've just driven a couple orders of magnitude of computation. And you can apply these ideas, I think, across a broad range of fields, including things like protein folding, drug design, and so on.
I think it's also important to point out that it's not about building that one exascale instrument, something I had mentioned previously as well, so that we can run that one application. It's much bigger than that, and it feels to me much more like the moonshot era of the 60s. There are 4 very concerted efforts globally toward exascale initiatives in Europe, 1 in Japan. There are motivating this which goes. I find one application that will scale efficiently to an exaflop. It's far bigger than that, and it's the movement of the IT industry towards massively scaled out systems and the absolute critical need for us to develop the technologies to build those systems. I'd point out again, we have an exaflop system today. It consumes over 650 megawatts of power. That's reaching the limits of a very large nuclear power plant just to power our top 500 HPC systems today. And that many, not only at HPE, but many in industry and many globally believe that there is an insatiable demand for computation if we can drive down the cost, drive down the power requirement, and drive up the productivity. And that the world will be a better place if we can do more HPC and more simulation of physical phenomena. And so the real underlying push here is to drive the technologies to make the stuff more accessible.
Well, I'll just exceed granted 20 million hours of compute, but had over
So scale out, not just scale.
HPCG or the green 500 that the top 500 does. Applications, I mean, we already have exaflop. We apparently are a TensorFlop. How is there tell us when we've arrived at the flag?
Over the last as a focal point for a while, target that number for a machine that could solve problems and have generality. So if you look at the exascale, they're not a peak exaflop. A multi application performance baseline on an existing, I believe, is a good efforts in the industry. And other industries have their proxies as well. At the end of the day, what really matters is how much faster see any benefit can truly represent that.
I agree. PAC is just a metric, and it's one of many. Who has purchased a car, you can open up right? You don't do that. But that metric of how much that car weighs does tell you instinctively something, some characteristics of the car, how it's going to handle, what its gas mileage is going to be. It is a metric. Am I going to go and make that my primary selection metric when I buy my? No. But is it a valuable metric? It's one of many, yes. And so that's how it is treated. I don't think really metric, but it is one metric, just like the weight of your